Dear students, a very warm welcome to MOOCs, massive open online courses on SWAYAM in chemistry. I am Charu Maini from DAV Public School, Sector 49, Gurugram. In this session, I will be presenting the third module on the chapter General Principles and Processes of Isolation of Elements. After going through this module, you will be able to appreciate the need for refining of metals, enlist different methods of refining of crude metals, and select specific method for refining according to the properties of the metal. In the previous modules, we have learnt about concentration and extraction of metals from its ores. A metal extracted by any method from its concentrated ore is usually contaminated with some impurity. Impurities present may reduce electrical and thermal conductivity of the metal, and it is not suitable for use in the industry as such. The impure or crude metal obtained after reduction of the ore may contain some residual unchanged ore, some other metal present in smaller amount in the ore, residual slag, flux, etc. left after smelting, non-metals like carbon, silicon, phosphorus, sulfur, etc. For obtaining metals of high purity, several techniques are used depending upon the difference in the properties of the metal and the impurity. Some of them are distillation, liquation, electrolysis, zone refining, and vapor phase refining. Now let us understand these methods in detail. First of all, distillation. You have studied about distillation as a simple technique for separation of a mixture of two or more miscible liquids. Similarly, this method is very useful for metals with low boiling point, that is metals like zinc, cadmium and mercury, which are easily volatile. The impure metal is heated in absence of air in a retort. The vapors are condensed and collected in a receiver, and the non-volatile impurities are left behind in the retort. The impure metal is evaporated to obtain the pure metal as distillate. Let us understand the process. The metal to be refined is heated above its boiling point. Impurities do not vaporize. Pure metal vaporizes and is condensed. Impurities are left behind. The next method is liquation. This method is used to purify metals having a low melting point like bismuth, tin, lead, mercury, etc. The impure metal is made to flow on a sloping hearth of a furnace and gently heated in an inert atmosphere, that is, absence of oxygen. The impurities, which are less fusible than the metal, are left behind on the top of the hearth, whereas the fusible metal flows down. In this way, metal is separated from higher melting impurities as shown in the figure. The process is the metal to be refined is placed over the sloping hearth of a furnace. The temperature of the furnace is maintained slightly above the melting point of the metal. The pure metal melts and flows down. Impurities having higher melting point are left behind. Next process is electrolytic refining. In this method, the impure metal is made to act as the anode. A strip of the same metal in pure form is used as cathode. They are put in a suitable electrolyte bath containing a soluble salt of the same metal. The more basic metal remains in the solution and the less basic one goes to the anode and drops as anode mud. This process is also explained using the concept of the electrode potential, overpotential and Gibbs energy, which you have studied previously. The reactions are: at anode, the metal gets oxidized to form metal ion and releases electrons. The electrons travel through the wire, and at cathode, the metal ions pick up these electrons to form metal. Copper is refined using this electrolytic method. Anode are of impure copper and cathode as pure copper strips are taken. The electrolyte is acidified, solution of copper sulphate, and the net result of the electrolysis is transfer of the copper in the pure form from anode to the cathode. As in the reaction, anode impure blister copper is taken, at cathode thin sheets of copper, and electrolyte is an aqueous solution of copper sulphate containing little amounts of sulfuric acid. The reaction, at anode copper gets oxidized to copper ions plus 2 electrons, and at cathode copper ions pick these 2 electrons to form pure copper metal. On passing electric current, pure copper metal from the electrolyte solution deposits on the cathode. At the same time, an equal amount of impure copper dissolves from anode into the electrolyte solution. The metallic impurities present in the blister copper drop down and deposit as anode mud, which contains antimony, selenium, tellurium, silver, gold and platinum. Recovery of these elements may meet the cost of refining. Zinc, silver, aluminium and lead may also be refined in this way. The metals obtained are of very high purity of the order of 99.9% purity. The second method is zone refining. This method is based on the principle that the impurities are more soluble in the melt than in the solid state of the metal. A circular mobile heater is fixed at one end of the rod of the impure metal. The molten zone moves along with the heater, which is moved forward. As the heater moves forward, the pure metal crystallizes out of the metal and the impurities passed into the adjacent molten zone. The process is repeated several times and the heater is moved in the same direction. At one end, impurities get concentrated and the other end is cut off. This method is very useful for producing semiconductor and other metals of very high purity. Example, germanium, silicon, boron, gallium and indium. Next method is vapor phase refining. In this method, the metal is converted into its volatile compound and collected elsewhere. It is then decomposed to give a pure metal. So, the two requirements are the metal should form a volatile compound with an available reagent, and second, the volatile compound should be easily decomposable so that the recovery is easy. Following examples will illustrate this technique. Mond's process for refining of nickel. In this process, nickel is heated in a stream of carbon monoxide forming a volatile complex nickel tetracarbonyl. So, nickel plus carbon monoxide when heated at 330 Kelvin to 350 Kelvins form tetracarbonyl nickel. The carbonyl is subjected to higher temperature so that it is decomposed giving the pure metal. Tetracarbonyl nickel when heated to 450 to 470 Kelvins decomposes to give nickel and carbon monoxide. The reactions of Mond's process as discussed can be seen in the flow chart, like the impure nickel reacts with carbon monoxide to form tetracarbonyl nickel, which is further decomposed to form nickel and carbon monoxide. Thus, you may see that the carbon monoxide is recycled in the process as shown. The next method under this category is Van Erkel method. This method is used for obtaining ultra pure metals for refining zirconium or titanium. This method is very useful for removing all the oxygen and nitrogen present in the form of impurity in certain metals like zirconium and titanium. The crude metal is heated in an evacuated vessel with iodine. The metal iodide being more covalent volatilizes, and as in the reaction you can see zirconium reacts with iodine to form zirconium iodide. The metal iodide is decomposed on a tungsten filament electrically heated to about 1800 Kelvin. The pure metal is thus deposited on the filament and zirconium iodide decomposes to form zirconium and iodine. Applications of ultra-pure zirconium and titanium. Zirconium is used as an alloy such as zircalloy, which is used in nuclear applications since it does not readily absorb neutrons. It is also used in catalytic converters, percussion caps and furnace bricks. The major end uses of zircon, zirconium silicate, are refractories, ceramic opacification and foundry sands. Zircon is also marketed as natural gemstone used in jewelry. The metal has many other uses, among them in photographic flash bulbs and surgical instruments to make the glass for television, in the removal of residual gases from electronic vacuum tubes and as a hardening agent in alloys, especially steel. The paper and packaging industries are finding that zirconium compounds make good surface coating because they have excellent water resistance and strength. Titanium can be alloyed with other elements to produce strong, lightweight alloys for jet engines, missiles and spacecraft, industrial processes, orthopedic implants, dental and endodontic instruments and files, sporting goods and jewelry. The main physical property of both titanium and zirconium, which belong to the same group, is that they are resistant to corrosion and have a high strength to density ratio. Now, let us understand the uses of these pure metals that we have formed: aluminium, copper, zinc and iron. First of all, aluminium, as we know, is used in aluminium foils, used as wrappers for chocolates. The fine dust of the metal is used in paints and lacquers. Aluminium, being highly reactive, is also used in the extraction of chromium and manganese from their oxides. Wires of aluminium are used as electricity conductors. Alloys containing aluminium, being light, are very useful. Uses of copper: we know copper is used for making wires used in electrical industry and for water and steam pipes. It is also used in several alloys that are rather tougher than the metal itself. Example: brass alloyed with zinc, bronze alloyed with tin and coinage alloy alloyed with nickel. Now, the uses of zinc. Zinc is used for galvanizing iron. It is also used in large quantities in batteries as a constituent of many alloys. Example: brass contains 60% copper and 40% zinc, and German silver contains 25 to 30% copper, 25 to 30% zinc and 40 to 50% nickel. Zinc dust is used as a reducing agent in the manufacture of dyestuffs, paints, etc. Uses of iron. The cast iron, which is the most important form of iron, is used for casting stoves, railway sleepers, gutter pipes, toys, etc. It is used in the manufacture of wrought iron and steel. The wrought iron is used in making anchors, wires, bolts, chains and agricultural implants. Steel finds a number of uses. Alloy steel is obtained when other metals are added to it. Nickel steel is used for making cables, automobiles and aeroplane parts, pendulum and measuring tapes. Chrome steel is used for cutting tools and crushing machines, and stainless steel for cycles, automobiles, utensils, pens, etc. So, let us summarize. For getting pure metals, we require refining. Refining process depends upon the differences in the properties of metal and the impurities. Several methods are employed in refining of the metal. For obtaining metals of high purity, several techniques are used depending upon the differences in properties of the metal and the impurity. Extraction of aluminium is usually carried out from its bauxite ore by leaching it with sodium hydroxide. Sodium aluminate thus formed is separated and then neutralized to give back the hydrated oxide, which is then electrolyzed using cryolite as a flux. Extraction of iron is done by reduction of its oxide ore in blast furnace. Copper is extracted by smelting and heating in a reverberatory furnace. Extraction of zinc oxide is done using coke. Several methods are employed in refining the metals. Some of them are distillation, liquation, electrolysis, zone refining, vapor phase refining. Metals in general are very widely used and have contributed significantly in the development of a variety of industries. So, these were the techniques for obtaining metals from their ores. I hope that you come up with some new techniques to contribute to the development of human civilization. Thank you.